Welcome to the November 2025 SJAA Imaging meeting. And tonight we have Francesco Meschia telling us about comet processing. Take it away, Francesco.
Thank you. Hi. It's comet processing because, as you know, we have two comets, maybe three, currently in the sky, or very, very recently in the sky. So maybe some of you have collected data, and a refresher on how to process could be useful. So let me share my presentation. Here we go. All right. How to cheat with comets. Oh, here. How to cheat with comets, aka how to process a comet in PixInsight. So, as we know, comets tend to come from far away, and they get closer and closer to the sun, following their orbit. And they are typically brightest when they are closest to the sun. They appear brighter to us when they are closest to the Earth, or a combination of the distance from the Earth and the distance from the sun. And because of the Kepler's law, they move fastest when they are near perihelion. And for us on Earth, they appear to move faster or fastest in some cases when they are near perigee, so closest to us. So this creates a problem, a conundrum that we have to contend with, because we want to image the comet when it's near perihelion, because that's when the tail will be longest. And the tail, although it may have some very bright parts, the outer portions are pretty dim, so you can easily compare them with a dim deep sky object that you may want to image. Therefore, we want long integration time. But if you're doing a long integration time with a fast moving comet, and it's fast because it's closer to the sun, you're going to have a comet that moves across the star field. And traditionally, when people were taking pictures on film or plates, astrophotographers have guided on the comet because they wanted to image with as much detail as possible the nucleus or the inner part of the tail, and they had to accept this. So the fact that if you guide on a comet, your stars will be trained. In many cases, if you're a professional astronomer, you may not care because as long as you have maybe some really well-defined beginning of the end of the star trails, so you can do astrometry. If you're interested in liaising with the comet, you don't care about the stars. But we care about pretty pictures, as we know. And so how to obtain a picture like this in which there are neither trailed stars nor a trailed comet? And the answer is that you cheat, because an image like this one is actually produced by combining two images, one of the comet alone and one of the star field. This brings the question: how do you do this? Because so the comet moves, the stars move at different speed, so neither of these two images that you plan to combine should be easy to obtain. If you obtain one, you're not going to obtain easily the other one. So we need a way to separate the comet from everything else. If we have a way to do this, then we can have a series of images, and we can register the images using the comet nucleus as the registration point. And then you integrate them. So you bring out the dim part of the tail. Then in parallel, you register the rest. So your star field without the comet, you register it on the stars, combine the integrated comet with the integrated rest, and you obtain the picture that we saw in the previous slides. This nowadays, you can probably the first thing that people think of is to use one of the neural network-based tools that we have, like StarNet++ or Star Exterminator, to separate the stars from non-stellar objects. But this used to be possible even before StarNet++ arrived. it is possible. It's just more tedious, and it leverages some properties of the images that you can collect when the comet moves at a different rate from the stars. Let's see more with some more detail how. The idea of the traditional workflow, the one that you see documented in all the sites that refer to the plane peaks in sight, is to you take a set of star-aligned subs. So you calibrate, you register just like you would do for deep sky objects. You can use a weight WBP or a star alignment manually as you prefer. Then you use a different tool in Peaks Insight, not star alignment, but comet alignment, to produce from these an equivalent set of subs that are comet aligned. But of course, they are comet aligned, but they have stars. And so you're going to have to integrate these comet aligned stars using a very aggressive pixel statistical rejection so that the stars are eliminated by the rejection process. In this way, you obtain more or less easily, depending on the conditions, a comet-only image. Then you're going to use, again, the same comet alignment tool, but in a different operating mode to subtract, literally, mathematically subtract the comet-only image from each of the star-aligned subs, the one that WBP put out. You integrate the comet subtracted and star-aligned subs, and you obtain the integrated rest that we were referring to in the previous slides. Finally, you combine the two integrated images, and at that point, is no longer comet processing, is a regular deep sky object image processing. So you use the same tools that you're already familiar with.
Hey,
it's easier.
I was going to ask, the last two things, well, not the last one, but the second to last one, you could take a picture of the stars after the comet's gone too, or before the comet's there.
And actually, it's something that I always want.
Yeah.
Sorry?
Is that cheating any more than this?
Well, no, it's. I don't see why it is not any worse than this. I always wanted to try, and I never tried for lack of time. But yeah, it's certainly possible.
Right. It would seem much easier, at least for that, for the star part, to just.
Yeah. You needed to wait for the comet to go away, or you need to have some reference imagery of the area. But yeah.
And then, of course, you take one of your subs with stars and comets, and you make sure that you place the comet properly, right? Like,
yeah. I mean,
otherwise you can put the comet anywhere in the sky.
Exactly. So this is one of the things that we're going to see tonight, because you have the problem of placing the comet in the right spot, even if you do the standard cheating 1.0, the basic workflow that I describe here. Yes.
Okay, thanks.
So just for as a form of clarify what I'm talking about, I'm going to show a little animation of the blinking of a series of 10 subs. The comet, this is the A6 Lemon. As you can see, it's actually 4 images. It moved quite a bit. 1, 2, 3, and 4. So if you use the comet alignment tool to realign these images, not on the stars, but on the comet, then you can obtain a set of images that looks like this. And this is just a magnified version. Look at what the stars are doing when I blink these pictures. 1, 2, 3, and 4. So the comet remains in the same position in the frame, and it's the stars that move. Now, if I do image integration on this exact 4 frames, I'm going to obtain this. Look at the stars are gone, because from one image to the next, the image of the star does not fall on the same pixels. And so they can be very effectively removed by, in this case, I think I used Sigma clipping, but there's many algorithms that you can use. And this is made very clear if you ask image integration to produce a rejection map. because the rejection map will look like this. You see where the stars are in each of the frames, and they did not, because of this, they did not make it to the final image. Now, this is the basic idea. And once you have this, you're going to use comet alignment in this mode, in the subtract mode, using the integrated image of the comet as an operand. Comet alignment will remember the offset of the comet in the star register frames from one image to the next, and it's going to translate the comet, interpolate as needed, and subtract it, so that you're going to get something that looks like this: 1, 2, 3, and 4. There is a little bit of a residual. In particular, there is for this set of images of Comet Lemon, because the comet was getting very low on the horizon as I was imaging. And so the proportion of the brightness proportion between the comet and the background sky changes quite a bit because of the atmospheric extinction. But already, if you integrate this, you can obtain an image like this one, which is pretty good already. It's there's some residual, but it's something that you could easily remove with a little bit of painting, clone paint tool in PixInsight. That's easy. And this is basically it for the slides. What I want to do now is to show how this process works in real life when we do it, when we apply it in PixInsight. So this is what we want to achieve in the end. I just want to mention that this is what I call the traditional workflow. There is what I call the modern workflow that uses some of the tools that are available now to produce, to make it easier to produce these starless images of the comet, and to make sure that even though the comet is moving, and even though the comet is getting closer and closer to the horizon, which usually happens because the comets tend to be closer to the sun when they are interesting, you can still normalize them in a way to make sure that the integration does not go completely out of kilter and invent weights that are not reasonable. So what you do with a modern comet workflow is to use a WPPP or your preferred method to obtain a set of registered images. Then you normalize them. And by normalized, I mean calculating the scale factor of each of them, which has something to do with essentially the statistical dispersion of the pixels in the image, and also equalize them by in their location. So the median value to be roughly the same across the entire stack. Once you have these normalized images, you can split this is where the process splits. With the comet, for the comet, you're going to comet align the subs. When you have obtained a set of comet aligned subs, you're going to use one of the star removal tools, for instance, a star exterminator, to remove the stars from each of the subs. And then in this way, you're going to get a set of comet aligned starless images, which you'll be able to integrate by using the weights that come from the normalization process and the comet aligned starless subs. You probably will need to use some form of mask, because the core of a comet tends to look awfully like a star. So many of these tools, Star Exterminator certainly, tries to remove the core of the comet from your image, which is not something that you want. So you're going to have to mask it to prevent the neural network from removing it. But once you have done your integration, you're going to have a comet master, so the image of your comet. You're going to subtract it from all of the normalized subs that we prepared earlier. In this way, you're going to have a set of comet subtracted and star aligned images, which you're going to integrate. and finally combine with the comet master that was produced in the previous stage. This will lead you to have a finished master for for the comet for that particular filter that you used if you're using a mono camera. If you're using an OSC camera, you only need to do this once. With an LRGB workflow, you do it 4 times for L, R, G, and B. So it's I imaged the last comets in LRGB simply because I don't have an OSC, and so either I don't image or I go through the pain of LRGB registration and the processing of the comet image. So now we can actually go to PixInsight. So let me stop this sharing and share PixInsight instead. Here it is. You can see my PixInsight. Hi. Hello.
Sorry, I couldn't find the unmute.
Oh,
yes,
okay.
Good.
Okay, it's working. Okay, so this is the Comet 2025 R2 SWAN, which I imaged on October the 18th. And the comet was crossing in front of the M24 star cloud. And this is what you're seeing here. That gradient from left to right is not the light pollution gradient, it's a Milky Way gradient. So let's see how we started. I have preserved for this demonstration all of the subs and intermediate processing artifacts that were produced by all the tools. So let's take a look first at the images produced by WBPP, which in my case are under the registered directory. I'm going to start showing you the blue ones. So this was a relatively easy case because the comet was not was pretty far from the sun in angular terms, and so did not appear to go down as dramatically as Comet Lemon did. So I'm going to now start the blink process. I have not essentially blink process has calculated the STF for the first image is going to apply to all of them. So this is a good tool to judge how well normalized or denormalized these images are. So let's start. Yeah, not too bad. They are pretty similar in the way they look. If we want to understand better what I'm talking about, let's take the histogram transformation tool. Let's zoom in a little bit. And yeah, this is the distribution of the background of one of these images. Now let me go to the next, and the next, and the next, and the next. They are roughly the same. They are not very, very much the same. So what? I could... what's that? Probably nothing. So this is good. It means that we probably don't need to do anything special to normalize these images. However, if we wanted to do that, we could. For instance, let me show you what my normalized images look like. Yeah, these are, as you can see, the background that really changes very little this time. It's very well equalized. How did I normalize this? So I used this tool in PixInsight called image container. An image container is what the name suggests, is a container of images. You're going to put anything, all the images that you want to process in a batch in this container. So in this case, it's all of the luminance images. And you're going to decide that any process that you drag onto this container will be applied individually on each and every one of these of the images that make the content, and the output will be recorded in one directory that you indicate. In this case, normalized L, because that's what I normalize. But what is the process that you do, that you apply? Well, the process that I applied was actually, I believe it's this one. Oh, yeah, was basically, no, it's not, sorry. Not this one either. No. And not this one. Oh, no, it was just the AB, so the automatic background extractor with the polynomial degree of 1, so that I would remove the linear gradient. So you do it by saying function degree 1, and then you drag this icon onto the image container, and this will apply to each image inside the container. I'm not going to do it now because I've already done it. It's those normalized images that I showed. Now we need to register the images, because right now they are star registered, and the comet appears to move when I go from one to the other, and you can see it moves quite a bit. Definitely not something that I can ignore. So we need to comet register them. We do it by invoking the comet alignment process. In the comet alignment process, I can add my comet images, and these come directly from the normalized directory where I saved the normalized images. You can see here. But before we can apply this process, we need to tell the tool where the comet is, in each of the images. Actually, I don't need to do it in each of the images, because assuming, and it's a reasonable assumption, that the movement of the comet for a relatively short time like this, about an hour, is linear, you only need to point to the comet in the first one and in the last one, and the comet alignment knows from the metadata of each of the subs when it was taken, therefore knows the delta t, how many seconds have elapsed from one to the other. So you click on an image, it opens here, and you're going to click on the core of the comet, what you believe to be the core of the comet, and the tool will actually do some PSF fitting operations. So if I click on a star, it will center it on the star. This is what I'm doing for I click on roughly the core of the comet, and the tool will actually precisely nail the centroid of the distribution of light. I did it for my first image, then I have to do it for my last image. Same thing. You click, and it finds the comet for you, the centroid for you, and in this way, the tool was able to calculate the delta x and delta y position in pixel coordinates for each of these images. If you want, if you don't have 60 images, for instance, if you have just a few, you can actually do it for each of them. This could be useful if the comet is so close to the sun that the trajectory is not linear, even in a short time, and it shows some appreciable curvature. So you may want to do that. There's another thing that I want to point out. You see that my comet alignment tool here has all B subs, so all blue filter ones, but there's also one L sub. What is this L? Well, this is an LRGB image. So I'm going to repeat this comet alignment on the G, the R, and the L subs separately. Now, if this begs the question, what is the reference point of all these images? And just like you were saying, how do you know where to place the comet? So you decide that one position that you like will become your pivot. It will become your reference frame, to use the terminology, not pivot. So in this case, I had decided that this particular frame of my luminance sequence was the was my reference point. This is highlighted by this arrow here. And the other thing that you need to do is to also point and click on the comet core for the reference image. Once you're done this, you can process everything using the apply global icon. I recommend using a relatively soft interpolation algorithm. This will need to be interpolated because all these delta are calculated with 2 decimal points by PixInsight. So we're talking about fractions of a pixel. There will need to be an interpolation. If you use the default interpolation is something probably a lens 3 or 4, you're going to have a very hard edges of the stars. And considering that they've already been interpolated once when WPP registered them to the stars, you don't want to overdo this. My recommendation is to use the Mitchell neutral valley filter, which is pretty soft, not very aggressive, and it works really well. The other thing that you may want to do is to click this compute PSF fits in checkbox. If you hover the mouse, it's going to tell you what it does. Basically, we compute for each target image, even the ones that you did not pick for manual registration. We'll compute the PSF, and so we'll improve the accuracy of this shift process and the translation process by looking individually in the frame where exactly the center is. And it may be a fraction of a pixel of difference, given that we're talking about 2 decimal points, decimal figures. So once you execute this, the output, you also needed to tell where the output goes. This is the comet alignment tool. You see it here. I typically to output into a directory that I create called comet alignment inside the temporary directory where WPP puts all of the temporary files. And inside the container of the type of image, in this case, comet aligned, I create one subdirectory for each filter. So I have comet align B, comet align R, comet align G, and L. Let's take a look at the registered blue frames now. You can see this is my temp directory. Some of the calibrated frames are the ones that WPP created. The register also created by WPP, but comet aligned are the output of the comet aligned process. So let's see how well it did. Okay. They don't seem well normalized. I might have done something wrong, but they certainly are they are registered to the comet. If I zoom in, the comet does not appear to move in the frame. Okay, that's good. So at this point, I would be able to integrate these images by using image integration. Now, the part of the normalization process, I mentioned that it does 2 things. One, it moves the median of each individual images to a common median. The other thing that it's important to do is to calculate the scale of each image, where scale is the statistical dispersion, is a measure of how noisy your image is. And this is important because when you do image integration, normally you put your images and then you say that you want to weigh this by SNR. Now, SNR typically is calculated in PixInsight by looking at the stars. And if you don't have stars in this, if you still have stars in this image, everything is fine. But if you remove the stars into this image, we haven't done it yet, but you'll see, then you have a problem. So let me show you what would happen if I integrate these images without just saying that the SNR is my normalization, my weighing parameter, and by saying that I wanted to apply a pretty aggressive sigma clipping. clipping everything that sits more than 1.7 sigmas above or below the median. These are values that I just found by trial and error. So I want to see the rejection maps. I want to clip the low range because the clip low range means that anything that is below a certain threshold will not be considered for the rejection. And if you remember what our blinked images look like, there's a lot of black, yeah, because the comet moves a lot. And if the comet moves a lot, the stars appear to move a lot. And therefore, there must be padding. And in this case, it's padded with black. So we want to tell image integration to ignore black parts. Don't consider them as part of the statistical distribution, the statistical analysis for pixel removal. Now, if I start this process, I get this. This is the rejection map. Now, as you can see, there's a lot of noise that gets rejected. There's hot pixels that gets rejected, but there's also the stars, really clear. And this is the rejection low. So this shows what are the parts that were either ignored because they were below the threshold, and the threshold is 0 by default, or removed because they were, you can see here, there are some residuals of stars. So what does the integrated image look like at this point? It looks like this. So it's far from being perfect. However, we should not forget one thing. What I did to go from this to this was just to apply the automatic stretch function in PixInsight. And as you know, this calculates the stretch factor based on the statistical properties of the image, which tends to highlight the noise. Now, if you want to see more realistic representation of what this image looks like, we should probably apply the same STF that we were using when we were blinking the stars. So this one. So if I drag and drop the screen transfer function from the blink screen to this image, it's even worse. What's going on? This. Let me open one of them. Might be easier. Comet aligned. Now I can drag and drop. Fantastic. Sorry, this is not doing what I was hoping. But yeah, the idea is that although I know what's going on. So these images don't have the same median. So what I need to do is to apply the STF function, and transfer function. Look at the cursors. I'm not going to touch the cursor, this one, which is the how strongly stretched the image are, but I'm going to change this to try to move the median to be compatible with this one, more or less. So it's still pretty bad. There are lots of star residuals. So we may be tempted at this point to do something before we integrate these images. So can we apply star exterminator on the comet-aligned images and then integrate them? And yes, we can do it. It's very easy to do in Star Exterminator, although it's quite time-consuming if you have many images, because there's this nice button, Progress Patch. In Progress Patch, you're going to tell the tool that you want to apply on a set of files, output all of the starless files to a directory of your choice, optionally output the star-only files to another directory of your choice, optionally apply a mask. You remember what I said? You need a mask to protect the comet core. This is it. And you can decide to apply suffixes or not. When removing the star, you can do the unscreening method, which is useful if the image is already stretched. But given that we are working with linear images, because only in linear space you can do subtraction and addition of images, then we're not going to do it. Then you're going to just select the files, and Star Exterminator will start crunching these images. And I'm not going to do it now because it's slow, but ultimately it will produce this.
Hey, Francesco, if they
Yeah.
didn't have that batch option, could you have used your image container thing that you were talking about earlier?
Um, yes and no, meaning that you can do it if you don't care about the star-only images, which I don't particularly. But the image container does not let you specify two different outputs, or one for the star-only images and one for the starless image. So you can do it, but only for one of the two.
Okay, thanks.
Yeah. Let me show you what the starless images look like here. Okay, that's not bad. The removal has been pretty effective, it seems. I mean, there are some artifacts that you can see because of the Star Exterminator probably got fooled by these black areas. But if we integrate these images, we are still going to obtain a much better result than this. And I can show you now what the result looks like. It's this, which requires one word of caution. So you remember that I did image integration here by saying that, okay, I want to use the SNR weighing method. This only works if it can find the stars in your image, and if you remove the stars, this is not going to work. It's actually going to give the opposite weights that you would than the ones that you would like. So the solution is that you run a tool that calculates the statistical properties of each of the subs before doing this. You do it on the registered images, and this tool is any of the normalization tools available in PixInsight. So you could do it either with local normalization or with the optional tool normalized scale gradient, which is one of my favorite tools. And they are both essentially equivalent in what they do for this particular case. What we need is only to create some files called the X. Remember the extension, but you will be able to add them with this button here. Going to the register directory. Oh, sorry, wrong one. I messed up and I had registered in the wrong directory, but I can show you here. Yeah, you see here this X and ML files. These are the normalization data. It's actually an XML file. If you're interested, you can open it, and it tells PixInsight what was the level of noise in each of these images. When you do that, automatically this changes to local normalization, and for weights, you can choose one of these weighing algorithms. The one that I recommend is PSF Scale SNR, which uses the scale factors, so statistical dispersion, standard deviation, but it's in a robust way, calculated on the flux, calculated on the PSFs of the stars. So basically, during normalization, the local normalization tool or normalized scale gradients applies fits each of the stars that are used for the estimation with a PSF function, typically a Moffat distribution, calculates the flux in each of them, and that is the signal. And the noise is obviously just the statistical dispersion of the background. So can very effectively calculate an SNR based on the actual scale of the image. So you're going to add them here. integrate, and the output will be something like this. And when you do it on an image like this one, where you start with the starless images, the rejection maps will not look very interesting because there's no stars, and so there's not much to reject. Now, we're not done yet, because now we have an image of the comet alone. We're going to save it to disk. And it's this one. I have a comet only B. And then we're going to go back to the comet integration tool, comet alignment tool, sorry. Same parameters that I had used before, but I'm going to choose as the operand the image that I just produced, with only B. I'm going to indicate that this is a comet aligned image. I'm going to let it do a linear fit so that it's not very important for this comet, but it was extremely important for Comet Lemon. When the background changes a lot from one image to the next, it's important to to rescale the comet image to fit statistically the target image. And you do it with this click, with this checkbox. You're also going to say that you want to reject anything that sits significantly below the floor. The floor is 0.0030. You can see it in the status bar at the bottom of PixInsight. And so you're going to do something like this. In this way, sorry, 0.3. In this way, the process will not subtract anything in the black areas that are left uncovered by the alignment process. When you do this, you obtain a set of images like these. But subtracted. The comet, I don't know why the first one, oh, it's the linear, the luminance, sorry. You see the comet is almost gone. It's all but gone. It's not exactly gone because there's always some small inaccuracy in the normalization. But the important thing is that the position of the comet from one image to the next is sufficiently well spaced that it's going to be easy for the pixel rejection algorithm to actually remove this. So if I integrate this, I end up with something like this. This is the integration that you can see here. The comet is somewhere here, but the images have been removed. The images have been removed by the integration process and the pixel rejection process. So at this point, all I needed to do is to give this file image a proper name. And then, let me show you in the history, I simply add, well, I could do a very simple addition. Let me show you what it would look like. I add the comet B, but I also needed to subtract anything from the median value. It would do something like this, which is okay, but as you can see, has increased the noise in the outer areas. If I undo and redo, the noise has increased. So what I choose to do is not to clip, not to subtract everything from the median value, but I'm using a process like this one, which is slightly more complicated. Let me show you the entire. So basically, I'm saying if the pixel value of the Comet B image is larger than the median plus a certain value that I set in my symbols, 5 ADU, which need to be normalized to 65,536 because in PixInsight everything goes from 0 to 1. And I am far from the two edges where I had uncovered areas. Then apply the subtraction. Otherwise, don't add anything. So it's target T plus 0. if this condition is not satisfied. When I apply this, I obtain this image that has the comet has its tail, but doesn't have the noise that the outer areas have. How to find this parameter? By trial and error. You don't want to, if I use a much larger value of the B parameter, let's say 50, I'm going to subtract a significant portion of the comet halo. You see, there's no tail left. So you need to subtract as little as possible, but a value that still removes the noise that you find objectionable. Like I had used 5, and probably use 3 as well. Yeah, the noise is still pretty much at bay. And this could be our arrival point for the B image. Now take this, repeat it for R, for G, and for L. So you're going to get this for R, very different. The comet is green, it's not red. In green is going to look really nice and big. And in luminance, it's, sorry. Let me go back in history. In luminance, it's going to look like this. Not too bad. It's an intermediate stage. But yeah, at this point, you have this is like processing a nebula from this point onwards. So you're going to combine RG and B in an RGB image. Let me show you what it looks like. 251. This is the RGB image. Then you're going to calculate the plate solution for this image. And I personally apply the multi-scale gradient reduction tool in PixInsight. So this requires me to apply a spectrophotometric color calibration first. Then, oh, sorry, I apologize. This is not what I'm doing. I just I applied this spectrophotometric color calibration because I just want to see the colors of the image. What I was referring to, I applied actually in the luminance image, and it's a spectrophotometric flux calibration, not color calibration. So this is a relatively natural, whatever that means in this realm, color image. Then I process it by doing some blur extermination, noise extermination. Finally, I again remove the stars. Yeah, because I want to process the stars and the comets separately only when I go from linear to nonlinear. So the stretching will be done this way. This is the stretched RGB image. Then when I get to this point, I normally go back to the luminance image and I process the luminance image in a similar way, all the way to stretching it. Because at this point, I'm going to apply LRGB combination on the RGB image, which will give me something like this, which typically has a better signal to noise ratio than just the RGB image. And in particular, if you have a fixed allotted time, like you want to image, you can image for no more than an hour because then the comet becomes too low. This is useful. It's useful to invest half of your time in luminance and the rest in RGB, just because just to get to a better signal to noise ratio at the end of 1 hour. It essentially maximizes the SNR for a given allotted time. Then what I did was to recombine the stars after having stretched them. And I stretched the stars typically using this fantastic tool called the generalized hyperbolic stretch, highly recommended. It gives you a nice stretch which you can finely tune and preserves exceptionally well the star colors. To the point that then you can increase the saturation pretty much as much as you like, and you're going to obtain still a very natural result. This is the combination of the stars with the comet. Then you can tweak it to have the the background that you like. Yep, save it as a PNG or JPEG file and publish it if you are so inclined. It is unconsuming, as you can see. If you can do it for images, it may easily take not one evening of processing, but a couple of them. And the other problem that I have with this is that it requires a huge amount of disk space, because already you start with a temporary directory left by WPP, which may be in the order of, I don't know, 10, 15 gigabytes. Then you're going to add one additional set of images for each of the filters for the normalized version of the image. Then one additional one for the comet aligned version of the image. Then one for the comet aligned and star removed images. And finally, one for the comet subtracted image. So it easily doubles or triples the amount of disk space that you need to add. But this is only for the temporary files. Once the processing is done, what I normally do is to save the project in PixInsight and do not carry over all the temporary files. So they are not making it to my hard drive and to my NAS to use up my space. And this is a relatively easy version of the process. Processing Comet Lemon was much harder because the comet was changing so much in one night. If you have in 1 hour. If you have a little bit of patience, I want to show you what the A6 comet processing looked like. Close them anyway. Yes, go away the process icons. In the meantime, if there are any questions. We're almost there. This is the longest, the image that has the longest history, and so it takes the longest time to restore. All right, here we are. All right, let me show you what the registered images put out by WPP look like. It's directory. So I'm going to blink through these. Keep in mind that the same STF is applied to each of the images. So what you see is the variation from image to image of the background, the real one. Oops. So if I look at one or two of these individual images, it's probably the easiest. Let's start with this one. Let's pick the first one. Now I applied, each of them has its own SDF, so they are not exactly comparable. But as you can see, it looks like the comet is much dimmer from one to another, which is true because there's extinction of the atmosphere. But there's also another problem. Let me show you what these images look like even before WGP has registered them, just calibrated. And 36. I wanted. Right, the two images are very different. There's a big, I applied the same STF to both of them. This image, which was taken at 7:10 p.m. local, which is essentially 47 minutes after this one, the background is much brighter because the comet was going down. Also, if I apply this an auto STF to this one, you're going to see another thing. Both images have a left to right gradient, but the later image has a much stronger gradient than this one. So this is going to be a problem because remember, what we are trying to do is to create an integrated version of the comet aligned images. If you have variable gradients from the first image to the last, your image, your integrated image will have an almost unpredictable final gradients because it depends on how the comet moved and how strongly the gradient was varying across the sequence. So when you end up subtracting it, it's not going to remove well neither the gradient nor the comet. So my choice for this processing was to pre-normalize the images by applying let me show you. I think I have it here. Yeah, I took the image container and I dragged on it not just the automatic background extractor that I had done for the other comet, but one process container, which is composed of one run of the automatic background extractor with function degree 2, so basically a parabolic surface, which is by trial and error, I had found that this models pretty well this type of gradient. You don't want to go too high because then the background model will start following the tail of the comet, and remove the tail of the comet, which certainly you don't want. But you also don't want to be 0 or maybe even just 1 is not enough because it's not it's not a linear gradient. It's non-linear and depends on if this was a 400 millimeter telescope. If you're using a telephoto lens, it will be even less linear because you're gonna have a larger field of view. And after applying this on each of the images, I apply this expression with pixel math. Basically, I subtract from each of the images its median, and I add the image of a reference image, which is this one here. In this way, I am translating the distribution, the model distribution of each of the images so that they will become all comparable. They will all have the same median value. Once this is done, I can apply the comet alignment, and I will obtain something like this. Comet aligned. B. So you see the background is pretty uniform now, and it doesn't appear to change a lot from the first image to the last. What changes is the intensity of the signal of the comet. This was not very apparent when we were looking at comet SWAN because it did not change significantly its altitude over the horizon, but this one did. So we need to, in order to integrate the image, once I remove the stars, I really cannot rely on a PixInsight estimating the SNR by itself. I really need to use local normalization, which here an example. In local normalization, what you do is to set up a reference image, which is probably the best that you have seen by blinking your set, because you want to normalize everything to the best image. You're going to set up a scale with my camera, which is a 12 megapixel, the scale of 1024 pixels is pretty good. And I'm telling the tool to generate normalization data with the same output directory as the input files. And the input files, well, in this case, it's the R filtered frames, but I did exactly the same for the B filter frames. In this way, the output of this local normalization process will be that set of XML files that we have seen. And when I integrate them, I'm going to do something like this. Let me get the comet image, the history. So this is what the tool looks like when it's set up for to use local normalization. You see the N in brackets here. This indicates that image integration has a set of normalization files. Then by default, it tells you that this will be local normalization. This is the algorithm that will be used to make the images statistically compatible with one another. But given that I've already done it manually, I just say, okay, ignore the normalization for this, but don't ignore it for the weights. Use the PSF scale SNR that you find in the set of normalization files. Now, notice one thing. Here, I am integrating the stars removed stars, the images. So it's an image that I have registered to the comet, and then I apply the star exterminator. However, the local normalization file is the second file name in this black window. It is not from the stars removed files. It's from the register image that was produced by WPP. And this is intentional. So what I want to do here is to provide the image integration with a set of starless images, but ask to apply the normalization factors of the images with stars. And you can do that in image integration. It does not complain as long as you have not changed the file names for the various files. This is why it's important to store it in each set of image in its own directory. So comet aligned directory, comet subtracted directory, and so on. And in order to do that, you need to be careful that when you use the comet alignment tool, you don't want to have any postfix or prefix. You want the image to be exactly as the file name to be left completely alone. This will work really well and produce in the end this an image like this one. B. Which is again pretty uniform in the background, and yeah, it's a little bit noisy, but it's only 40 minutes of integration, so there's not much one can do except for using the luminance version that has a. If I apply the same SDF, you're going to see that has a much smoother, as usual. It's much smoother. When I do this, I'm going to obtain a final RGB image that looks like this. This is the starless version. And then I typically for this image, instead of adding the stars in PixInsight, I exported everything to Photoshop because I wanted to do some final adjustments of the saturation. But I want to show you the importance of using luminance image. So let me go back in history. So this one is the image just RGB. This is LRGB. Look at how much the large scale noise goes down from here to here, here to here, here to here. It's pretty dramatic and it's very useful in this case. If you have a unlimited time and you're not constrained by imaging your comet in a certain time allotment, by all means do RGB alone because you're going to have a better final data. But if you are time constrained, LRGB is the way to optimize. This basically concludes my presentation. Hi, let me stop sharing and yield it back to you.
Hey, all right. Okay, well, are there any questions? Well, I can supply a question to get us started then. I,
Yep.
uh, it has to do with the weighting of the integration. So let me ask it on both ends. Like one,
Yep.
why wait? Just why not just use them all? You want to maximize your data. On the other hand, I know from previous presentations you've made that you have this, at least at some point, you had this fancy way of weighting well beyond SNR. I forget the name of the guy who put that together, but you
Yeah,
followed.
it's I
So
think a
why not do
normalize.
that?
But I can do that. The problem with using a normalization tool like NSG is that you need to be sure that it only considers the stars that are not over the comet and does not consider the comet as part of the background model. And with a comet this big, with the SWAN, I could have done it, but with a comet this big, I was lacking a tool. I would have wanted a tool that I can, with a lasso, tell where the comet is, and then ask it just to ignore anything within that lasso. It doesn't have this ability, and so I decided to do it manually. But yeah, it would have been my
And
preference.
okay, so then the other end of that was, like you
Why
showed
wait?
RGB versus not. So what about waiting? Why wait at all?
Yeah, so let me show you one thing. If I go back to PixInsight for a moment, I'm going to use the tool called subframe selector to calculate, compare the various files that I produced. So the comet aligned B. Actually, not the comet aligned, the comet subtracted, the starless. So stars removed, B. I'm going to let it run. It takes a few seconds.
You should try it on 1,000 files.
Yes. All right. So if I use the standard algorithm, which is SNR, this is the way that image integration would weigh the images. This is the index. So this is the first image. This is the last. So image integration would give a much larger importance to the worst image than to the best.
Yeah, I said why wait? In other words, why not wait be one?
Oh, it's yeah. You can say ignore weight. Yes. Let me see. Let's do a comparison. So this is the comet B that we start with. And I do the same here, but I'm gonna say no weight, don't care. And I'm even gonna remove the local normalization files. So there's really nothing. Now let me apply the same SDF so we can directly compare them. Blink. It's not much. I see a change in this area here. The Comet B image has a brighter, uh, looks brighter in this portion. Let me blink it again. Yeah. And
Right.
if I go back to the frame selector and I add the normalization files here, I ask to calculate again everything. Now, if I look at my weighing metric PSF scale SNR is exactly 0. How come? Something must have gone wrong here. 0 again. Yeah, it's 0 everything.
If you had a weight of 0, you wouldn't get an image.
No, exactly. This is only happening now. This is the type of a
Okay.
way that I would see. And if you see here, these are not normalized to 1. So the highest weighted image is 3 in 10 to the minus 3. And the lowest is 5 in 10 to the minus 4. So it's 6 times. 6 to 1 is the ratio of weights. So it's pretty important to have it, I think. As you don't want this image, which is noisy and has very little signal, to be counted as much as this one.
Right. I guess. I mean, assuming it's not good, assuming you believe the weight. But yeah, you showed, I guess, that it did improve the image.
Yeah. Not much, but a little bit it did.
All right. All right. Thanks.
Yep.
By the way, one other question.
Yeah.
Have you ever tried shooting multiple nights a given comet?
No. In particular, I think it would not be a good idea for this lemon because the tail changes a lot, even just in 1 hour. If I blink let me blink through the L frames, you're going to see that there are changes in the structure of the tail in 40 minutes.
Yeah, I mean, I saw that GIF that I mailed out.
Oh, yeah. The one that you sent. Yeah, okay.
Right. So, yeah.
It's much better than mine. Yeah. So yeah, I think that if you do it over 2 nights, there's no chance that the tail will be comparable from one night to the next.
So something like your first comet, though, it might have been doable, or if
yeah, it might have been doable.
Anything, or I don't know.
I didn't get that.
I'm just saying, but maybe you had enough data, or do you think it would have bought you?
Oh, so no, this one, the comets that the image of R2, I imaged it from the Los Padres National Forest, and I only had 1 night available. So even if it did not, the idea did not cross my mind, but even if I wanted, I didn't have the time to do it.
All right. Okay, are there other questions?
I have both one-shot color camera and monochrome. And after watching your processing tonight, I'm pretty sure I would choose the one-shot color.
Absolutely.
It would simplify things tremendously. I don't know how the result would be. Would the result be better or worse?
I think it's going to be similar to the RGB image. You wouldn't have the advantage of luminance, which is the fact that it collects photons from all across the spectrum in one shot. But I don't think there would be much difference if you compare your result in OSC with my RGB only. And it certainly is much, much more convenient.
Well, thanks for a great presentation tonight.
You're very welcome.
All right. Well, it doesn't sound like there's other questions. So thank you very much, Francesco.
Thank you, Hai, for having me, and everybody for the patience.
Yeah, and we'll see everybody next month to hear more about Nina. So
thanks, Francesco.
Thank you, Francesco.
You're welcome. Thank you. Bye.
Good night, everybody. Great to see you.
Likewise.